Okay, welcome. This is 740 Graduate Computer Architecture course, and this is the first video lecture which introduces the course, talks about the logistics, and talks about some background assignments. This is the agenda for this lecture. We'll talk a little bit about the syllabus, course logistics, information and requirements. I'll talk a little bit about the online nature of the course, or the hybrid nature. We'll talk about the introduction to computer architecture concepts, what you will learn in the course, and I'll give you some background videos and lectures to study. The non-agenda will not talk about grading and policies. There's a separate video for this. We will not talk about the details on course project, although you will be aware that there is a course project in this course. And I will not talk about the details on paper review assignments. And there will be another video for initial assignments and homework. So these are all covered in separate videos, and you should watch them separately. First of all, course info. Who are we? My name is Onur Mutlu. I've been at Carnegie Mellon for 4.5 years, and this is my email address. Actually, maybe about 5 years now. This is my email address. Feel free to email me anytime. This is how you can reach me best. My office is at Collaborative Innovation Center, 4105. These are my office hours, or you can visit me by appointment. And this is my website. I got my PhD from UT Austin. I worked at Microsoft Research, Intel, and AMD before coming to Carnegie Mellon. And I'm interested in many things, and certainly on top of the list comes computer architecture, the course you're going to take, hardware-software interaction, and a bunch of other things within architecture and across areas spanning architecture, next to architecture. I do a lot of work on many core systems, memory and storage systems, looking at techniques to improve programmer productivity, looking at efficient ways of building interconnection networks. I look a lot into hardware-software cooperative techniques that try to provide better support for programming languages, operating systems, as well as overcoming the shortcomings that could potentially get exposed from the circuits downstream. For example, failures that get exposed to the upper layers of the system. How do we fix that? So fault tolerance is one of my interests. Hardware security is another of my interests. And I'm increasingly excited about algorithms and architectures for genomics and different kinds of embedded systems that require significant energy-efficient processing to improve system performance, as well as performance of important applications. So actually, these topics are the topics of this course as well, and we will get to talk about a lot of the fundamentals and research that's going on in these areas. So I'd be happy to talk about any of the topics if you're interested in not only the course topics as well, but also the research aspects of it too. These are active research areas in my research group. We also have some teaching assistants, some brilliant teaching assistants who have taken the course before. Tyler Huberty, Brian Osman, and Hongi Jin. They've all worked with me before. They've all taken my courses. And there will be one more teaching assistant probably, given the size of the course, unless we shrink the course at some point. So get to know them. They will interact with you both online and in person as well. Where can you get up-to-date course information? This is the website for the course, and pretty much everything will be posted on the website. And you should use that as a hub. It should be bookmarked on your favorite browser probably. This will contain the syllabus and contact information. This will contain the links to the videos and the online education site. This course will be heavily online. The lectures you will be watching will be online, and later I will talk about how that works, but all of the videos, it will be accessible through the website. You'll get the lecture notes, all of the slides, again from the course website. Readings will be posted there, and there will be a link to the review website. You will be doing some paper reviews. And project information, which will be extensive, will be posted there. So any information related to the course, we will try to keep the website as up-to-date as possible. So bookmark this website. You will get some information from Blackboard, and it will be linked from the website. And we will also have a link to the online education site, which we will discuss later. Your email, we will email you once in a while, potentially, and you should watch out for the emails coming from us. And you can also email us if you would like to get some up-to-date course info that's not available on any of these sources above. Basically, you can email us at 740-official@ec.cmu.edu, and this email actually goes to all of the TAs and myself, and this way you can, by emailing all of us at the same time, you can ensure the fastest response time possible. If you email only one of us, then you may not be getting the fastest response time because you're not exercising the redundancy that's available within the teaching team. This is a hybrid course. This is something everybody should be aware of, and you should go into it knowingly. Basically, it will be heavily online. There will be in-person recitations and office hours. Of course, this doesn't apply to remote students who don't come here, but these in-person recitations and office hours will be available to students who are here. Remote students will be able to do the same thing online. But except we haven't invented I guess virtual reality fully yet, so you may not be able to have the same feeling, but we'll try to get you the best education possible. Basically, lectures will be fully online. What does this mean? The purpose of the lecture is to learn the basics of a topic, and I will be giving a lecture like this and recording it and posting it online, and you're expected to watch all of the lectures fully as assigned by the due date, and it's important so that you can actually learn the material, learn the basics of the topic. And videos and supplemental material will all be linked from the website. Readings will be online to supplement this. The purpose of the readings is to enhance your understanding of the material beyond the lectures. And this understanding is not only on the fundamental concepts, but we will assign you readings from cutting-edge research so that you get a good sense of not only the fundamentals, but also what's going on in this hot area of computer systems and computer science today. You're expected to do the readings before the due date, and some of the readings will be assigned as reviews, and you're expected to enter reviews on the review website, and there will be more information, a separate video for this. The recitations, on the other end, will be both in person and online. If you look at the course syllabus and CMU course schedule, you will see there are 4 slots assigned for this course, and those are actually for recitations. They're not for lectures, because lectures are online. And the purpose of the recitations is to enhance understanding via deeper discussion. So this is where you get to ask questions. This is where we present additional material, and this is where we have discussion. And hopefully, if you've done the lecture, if you've watched the lectures, done the readings, then there will be a discussion that's much more advanced than possible without the online nature of the course. These will happen during the specified times in the syllabus as well as the course schedule. You can take a look at them, and the locations will be specified as well. And we will announce the recitation times and format weekly. If you look at that, there are, I believe, 7 hours of recitations scheduled right now, or maybe 8 hours of recitations. Of course, we're not going to have 8 hours of recitations, but these times are scheduled so that we can flexibly and dynamically schedule some of the recitation sessions so that we can accommodate both students here as well as online students. And in-person recitations, whenever we hold a recitation session in person, and we're planning to hold some of the online recitation sessions as well, where online everyone can join, these in-person recitations will be recorded and posted online as soon as possible so that remote students and students who cannot attend can have access to these. Okay, so that's the summary of the hybrid nature of the course. Basically, get used to the online website as soon as possible. Lectures will be online, and I'll give you some assignments so that you can get used to watching some lectures online too. Office hours on the other hand will be both in person and online. The purpose of office hours is to clarify unclear points and delve deeper into the topics. Locations and times will be posted, and myself and all of the TAs will have office hours. And sometimes these will be held online. Sometimes we won't be available in person. So we're expecting every one of you to use the technology that's available. And I'm hoping that you all are much better than me at the use of technology. In fact, maybe you'll teach me how to use this technology so that I can be a better teacher online. Okay, a note. Since this is actually one of the first courses that has moved into hybrid education, online plus offline education at the same time, we would like to get your feedback. Please provide us any feedback with the online lectures and quality of the online environment. What works for you? What doesn't work for you? We'd like to ask for your feedback. We will give you a feedback sheet at some point, but this may be late. If there are any issues at any point in time, we would like to know these early so that we can react to them and we can make this experience much better for you so that you can get the most out of it. This is especially true if you are remotely attending the class, because you're remote and we don't have in-person interaction, so you should notify us as soon as possible if there are any issues related to the online nature of the course. But we do want this feedback, and this is very important going forward in how we design the courses that are hybrid and that are mostly online. So what will you learn? A little bit about what you will learn. Well, hopefully you're all here to learn about computer architecture, and hopefully you all had some exposure to computer architecture before. So what I put up on this slide is not necessarily something new for you. Computer architecture is actually the science and art. In fact, it is potentially more of an art than science of designing, selecting, and interconnecting hardware components and designing the hardware and software interface to create a computing system that meets potentially many different goals: functional goals, performance goals, energy goals, cost goals, perhaps reliability goals today. Basically, it's a science and art. Why is it art? Because it's really dependent on many factors. And you're designing a computer architecture, a computer platform for 5 years from now. You don't even know what the applications what applications will necessarily be running on this platform. And it's very difficult to model the future. And as a result, there are many choices that are made in computer architecture that are like art, that are based on insight, and that are less based on science, that are less quantitative, because it's very difficult to quantify what people will be running on a computer platform 5 years, or maybe even 10 years from now, or maybe even 2 years from now. That requires correct or accurate modeling of the development of applications that will be available 2 years from now, or maybe 5 years from now. And it's not clear if we have methods to do that today. That's why a lot of computer architecture is actually science, is actually somewhat of an art. But there are scientific parts of it too, and we will look at both parts of computer architecture. The traditional definition of computer architecture, on the other hand, I've used a non-traditional definition right here, but the traditional definition is more strict. And this is the definition from Gene Amdahl. Gene Amdahl was one of the designers of the IBM 360 computing system in the 1960s. This was IBM's flagship supercomputer at the time. And his definition in IBM Journal of Research and Development was basically architecture is the attributes of a system as seen by the programmer. Basically the conceptual structure and functional behavior that's exposed to the programmer, that's different from the underlying implementation, which is as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. Basically, the traditional definition of architecture is the interface that is exposed to the programmer. This is basically instruction set architecture, whereas underlying implementation is more microarchitecture. So these concepts are hopefully already familiar to you. If they're not, you should definitely watch the lectures that I will recommend at the end of this class. They're from 447, which is a prerequisite for this course, and we'll talk about that in a little bit. If you look at the levels of transformation, this is the level of transformation in computing systems. Basically, you take a problem, you convert it into an algorithm, and that algorithm gets programmed into some programming language by a programmer. And that program later gets translated by a compiler, dynamic or static, into the architecture, which is instruction set architecture. And that programming language also, that program also gets run on the system using a runtime system. And microarchitecture is the implementation that actually executes that actually satisfies the contract between the programmer and the hardware, which is actually architecture. And microarchitecture is built upon circuits, and circuits use physical principles to operate. And there's a user in between everywhere. That's very important. I put it over there because we're actually in the end designing these systems for users, so it's important to keep that in mind. If you look at computer architecture traditionally spans the ISA level, instruction set architecture, as well as the microarchitecture level, basically how the underlying circuits that satisfy the programmer's contract with the hardware operate. And computer architecture also spans a little bit the runtime system, the support for the runtime system, the operating system, the memory management functions. For example, power management functions that are available in existing architectures are actually support for the runtime system. And potentially it could extend a little bit below microarchitecture as well. So in this course, we will mainly focus on these two layers, but I would like you to keep in mind the other layers also, because the other layers, everything above the red circle over there, and a little bit below the red circle over there, actually is affected by computer architecture significantly, and they also affect computer architecture significantly. So we'll look at the interaction between the runtime system as well as the computer architecture. Programs, for example, can be optimized differently for different architectures. This is very well known. And we'll look into some of that, how you can also design architectures that can execute some particular programs fast and some other programs very efficiently. For example, one of the research areas my group is looking into is accelerating genome sequence alignment. And if you can design computer architectures that are relatively specialized to execute these programs, maybe you can design a much more efficient system for these programs. And we will talk about some of these specialized architectures. We'll talk about accelerators at some point in this semester. And also, if you look at this, the blue circle spans below the red circle. Circuits and technology significantly affect what happens in the architecture. Sometimes architecture is driven by the different circuits. For example, the 3D stacking technology enables very different architectures. If you can stack a logic layer on top of, underneath a DRAM layer, a DRAM chip, now you can have significant bandwidth between that logic layer and the memory chip. Now potentially you can move some computation to that logic layer from the processor. So this kind of technology, this 3D die stacking technology, can enable very different computer architectures. And this is true for other technologies as well. Later we will talk about emerging memory technologies in this course. And one of the emerging memory technologies in this course is phase change memory. Traditionally, we have had in the working memory of a computer has been built with DRAM, and DRAM is volatile memory. Basically, it consists of a capacitor and a transistor, and that capacitor loses charge over time, so it's volatile. But there are some other technologies which could potentially replace DRAM. They seem to be very scalable. For example, phase change memory is one example, and phase change memory operates in a fundamentally different way than DRAM. Basically, you store a 0 or 1 depending on the phase of the material. You heat the material, which changes the phase of the material, and you detect the resistance of the phase, which basically enables you to store and decode a 0 or 1. And this is non-volatile. And if this technology is available at the underlying circuits and technology layer, then the question is, how can you actually design a computer architecture that can take advantage of this non-volatile main memory, the working memory? We will actually pose this question in some of the project topics, as well as we will discuss some of the implications of non-volatile memories like phase change memory on computer architecture today. But basically, the takeaway is that even though computer architecture is traditionally constrained to that red box over there, you see, we would like to take a very broad approach. I would like you to think of the ways in which the upper layers of the levels of transformation affect computer architecture and get affected by the computer architecture, as well as how the lower layers affect computer architecture and get affected by the computer architecture as well. Okay, we'll get back to that a lot. And one of the lectures that I will strongly recommend you to watch as background material, the first lecture of 18447, the undergraduate computer architecture course, delves into the hardware-software interface and why computer architecture is important for both software layers as well as underlying hardware layers. So you will see more of that in that lecture. I would strongly recommend you to watch it. Okay, that no textbook really required should not appear over there, but that's okay. What will you learn in this course? We will learn the hardware-software interface, major components, and programming models of a modern microprocessor. We will talk about state-of-the-art as well as research proposals, and you will learn trade-offs and how to make them. So this is a course about trade-offs. Every time you make a decision in the design of a computer, you're making a trade-off. You're trading off one quantity with another quantity, and maybe multiple things. You're trying to potentially get the best of both worlds. And we'll talk about how these trade-offs are made and how different mechanisms actually potentially enable different trade-offs. Our emphasis will not only be on fundamentals, but we will also look a lot into cutting-edge research. Basically, today is a very hot. Today, computer architecture is a very hot topic in computer systems because it's not clear how you can design the best architecture today. People have moved to multi-core systems. There was a period in computer architecture where building a single larger core, pipelining it deeper, and trying to extract a higher performance from a single thread was the way to go. That was the paradigm of the day. But today, it's not clear because that approach doesn't scale very well. It's become much more complex to build an engine that's single core, that tries to execute the single thread much faster. So people have moved to multi-core architectures, but then there's a trade-off here. Now multi-core makes life much harder for the programmer, because now if you want to get performance, you need to parallelize your code such that it runs on multiple different cores. Now this is a problem because maybe performance of software cannot scale as easily, especially for those cases where it's very difficult to parallelize. This is why computer architecture has become much more interesting, because it's not clear what the solution is going forward in designing computer architectures. Perhaps you have many different specialized architectures. Perhaps you have a general purpose architecture that can support programs better, but maybe you add new support for programming and memory management. So these are issues that make computer architecture a much more difficult problem, a much more interesting field as well. There are also other issues on the technology side which push computer architecture to be important. One issue is the scaling of logic to smaller technology nodes has become increasingly difficult. And people are feeling this in memory, and we will talk a lot about this. Basically, technology scaling the minimum feature size of a transistor and CMOS logic has enabled a lot of benefits. Now you could put many transistors on chip. You could also increase the capacity of memory. You could keep it low cost, and you could also keep the energy scaling nicely. But going forward, and actually it has already become difficult to keep energy benefits as you scale the size of the circuits. It is also, for example, as you scale the size of a DRAM cell, it becomes much more unreliable. It becomes more leaky, so you consume more power. And the solutions that are required to enable the scaling to be much better has become very difficult at the circuit and device levels, which means that someone else at the upper layers have to tolerate these circuits that are not scaling very well. And guess what? Who that is? Architects are the first ones that are exposed to this problem, and designing architectures that can tolerate some of these scaling issues at the circuit level is a very interesting phenomenon. And it's not clear how to do that. As a result, there's a lot of research in computer architecture in these areas that are happening to figure out what are the best ways to deal with reliability issues, deal with power issues, deal with building very large capacity memories. And we will talk about some of these issues. So our emphasis will be not only on fundamentals, but also on cutting edge research, because this is an important research area going forward. You will also get a chance to do hands-on research in a computer architecture topic, and we will provide a list of topics. This is a semester-long project, and our focus will be on how to design better architectures, as well as how to evaluate some of the proposed techniques potentially. So if you would like to do an implementation and evaluation project, that's also okay. Now, ideally, we would like to find projects that are towards designing better architectures, generating new ideas. But since this is a large class, we'll focus on both types of projects. This is not an introduction course, so you should be comfortable with jumping into doing research and implementation in computer architecture. And you will also learn how to dig out information. Everything I told you over here is actually based on a lot of information, and you will benefit the most from this course if you actually dig out information on your own and take the information we provide and do more with it. There's no textbook really required. If you look at your syllabus, you will see that we don't require a textbook, but we will give you a lot of readings. So you will be definitely reading a lot in this course, and hopefully those readings will enable you to do better projects, and will enable you hopefully you will be able to use those readings in your research and other courses as well. Basically, see the syllabus. Syllabus has more detail on textbooks that are recommended, but you're not really required to buy a textbook. So one example of what you will learn, I will very briefly cover this because it's one of my favorite topics. But if you look at a multi-core system today, and this is not today, this is actually a very old multi-core system from AMD Barcelona, maybe 2007 or so, 2006 or so. It consists of multiple cores. And these multiple cores have some memory as well as pipeline in them that do out-of-order execution, which we will cover briefly. These cores have some private caches, L2 caches, and they also have some shared cache. They also go to the DRAM memory controller when requests miss in the shared cache. There's a DRAM interface, and there are DRAM banks. Basically, if you look at this, there are many parts of the core as well as the system that are shared among the cores. And one problem when you execute programs in such a system is this. You get unexpected slowdowns. This is actually based on an experiment we have done right now, 7 years from now. We call this the memory performance attacks. But let me tell you what the experiment was. We basically took two applications, MATLAB and GCC, and these are real applications. You might have used some of these, or all of these perhaps. Basically, we ran these two applications together, these are single-threaded applications, on a two-core system, and measured the slowdown each application experienced compared to when it's run alone on the same system. So MATLAB slowed down by 7% when it ran together with GCC, as opposed to when it was run alone on that two-core system. Whereas GCC slowed down by 3.04x, basically 3 times, compared to when it's run alone on the same system. Which means that when these applications are running together on a multi-core system, one of them is slowing down significantly, whereas the other one is not slowing down significantly. And the y-axis shows the slowdown over here. And this problem is not solved if you go and change the priority of these two workloads in the operating system. If you go and nice MATLAB and give it low priority and bump the priority of GCC high in the system software, if you do that, nothing changes. You get the same slowdowns that you see over here. Why? Because this was a two-core system, and the operating system scheduled MATLAB on one core and GCC on the other core, and there was nothing else running on the system, and they kept running. Even if you change the priority, nothing changed because the priorities are not conveyed to the hardware. The priorities are not used to deschedule applications either. So at that time, we called this the memory performance hog. There's a reason for this, and we will cover the reasons in a lot more detail than 447 in this class. We call this the memory performance hog. So why do you get a disparity in these slowdowns? Basically, this was the system we ran these two applications on. It consisted of a shared DRAM memory system. The cores shared the DRAM memory controller, the DRAM bus, and the DRAM banks. And when we ran these two applications, MATLAB and GCC, what happened was MATLAB and GCC both sent requests to the memory controller. MATLAB was very aggressive. It sent a lot of requests at the same time. GCC was not very aggressive. It sent only a few requests at the same time. But it turned out that the memory controller actually prioritized MATLAB's requests over and over while starving GCC's requests. So this was because memory controller was actually designed to be designed unfair. It wasn't really aware of these two different applications that are generating requests to it. It was trying to optimize for something else other than fairness or other than the progress of the cores. If you look at this, MATLAB's core progresses a lot, whereas GCC's core twiddles its thumbs. So this unfairness leads to these unfair slowdowns. And you may ask why this is the case, and some of you know why this is the case because you've taken my 447 lectures. And if you actually go and watch the 447 lectures, you will learn why this is the case. But we will actually go into detail of how to design these controllers or how to design the system to be much more fair. And this is a big issue today in multi-core systems because in multi-core systems you design many, you add many different cores into the system, and they share the caches and the interconnect and the memory controller. And at any point in time, there may be unfair policies, and these unfair policies cause some applications to slow down significantly. And if those applications are very important for the user, maybe you miss some of your deadlines. And if it's a hard real-time application. If it's a soft real-time application, again, you may miss some of the deadlines, and it may be important. For example, if there's a virus checker running, it's not really time critical. It should run when there's spare time to run in the system. But at the same time, if you're trying to watch a video that's really important to you at that point, and if that virus checker is hogging the DRAM memory controller just like MATLAB is hogging the DRAM memory controller, then your video may skip. You may not get the frame rate that you want from your video. So we will look at issues like this. Why does the disparity in slowdowns happen? Basically, understanding why this happens is important, and that's the subject of computer architecture. And we will cover this in more detail. This is just a teaser for you to read this paper. We've written this paper on Unix Security 2007 conference that describes the issue and describes the underlying causes. Even though we will cover this later, I would encourage you to read this paper. So let's take a look at the course goals. There are two goals in this course. First goal is to familiarize computer architecture students and those interested in computer system design with both fundamental design trade-offs and recent research issues and trends in computer architecture. What does computer architecture mean in this sense? Processor, memory, and platform architectures and their interfaces in both today's and future systems. So we'll have a strong emphasis on both fundamentals and design trade-offs, and I'll try to give you a historical perspective as well as what's going on in research today. The second goal, which is equally important, is for us to provide the necessary background and experience to advance the state of the art in computer architecture by performing cutting-edge research. So you will actually get that experience by performing cutting-edge research or implementing some research idea on your own and evaluating its trade-offs. So there will be a strong emphasis in this course on critically evaluating research papers, and you will do this through review assignments and literature reviews in your project, and also on developing mechanisms that advance the state of the art or implement some of the state of the art proposals. And this will happen through the course research project. So if we satisfy these two goals, you will hopefully be able to be on top of a lot of the fundamentals as well as research in computer architecture today, and also be able to have the necessary ammunition and background to perform cutting-edge research in computer architecture. And I would encourage you to do both, actually, to take these two goals to the heart and try to do cutting-edge research in your research project. And we will talk about that research project separately, but previous incarnations of this course have led to strong submissions to top conferences in computer architecture. And some of those submissions actually many of those submissions got accepted, and they were presented at top computer architecture conferences like ISCA, International Symposium on Computer Architecture, Micro, International Symposium on Microarchitecture, High Performance Computer Architecture, as well as ASPOS, Architectural Support for Programming Languages and Operating Systems. And these are four of the conferences that we will read papers from in this course, but we will also read papers from the systems area as well as underlying areas. This is a graduate level class. I'm talking about papers. Obviously, this must be a graduate level class, and we will treat you will be treated as graduate students, which means that you should seek feedback when you need to. So we won't necessarily give you feedback. You should seek feedback from us if you would like to, and we require some background also. So we would like you to know basic architecture, basic concepts. If you've taken 18447, that's the perfect prerequisite for the course. If you have not taken it, that's okay, as long as you familiarize yourself with the material and as long as you've taken some basic architecture course somewhere else. Basic compilers, basic operating systems, and programming skills. Programming skills are needed for most of the project assignments. You will determine your own project assignment, but you will need to know programming to do the projects. And importantly, we'd like you to have the spirit, excitement, and dedication for deep exploration of a topic in computer architecture and the topics in general. If you're excited about this, you will hopefully do well in this course as long as you put the effort that's needed and you have the background that's needed. So what do I expect from you? Obviously, you should learn the material, and not only learn the material, but also research it. I like finding the original source of ideas, so if you actually hear an idea that is discussed, go ahead and research it. Today, there are many ways of doing that, and you can actually generate a lot of different ideas by doing this. And I strongly encourage you to do that, not only in this course, but also in many other courses that you take while you're at Carnegie Mellon. Do the work and work hard. And this course will be difficult. It will require you to work hard, but it'll be a lot of fun also. And it will be important for you to dedicate the time for the research project. It may not look like it right now, but the research project will take a lot of your time, and there will be a lot of readings in this course. This will be a fast-paced course. So if you're not ready for it, please talk with us because this will require a lot of work. I'd like you to ask questions, take notes, and participate in discussion. Take notes while I'm talking and ask the questions during the recitations. And recitations will be more of discussion style. We may discuss papers. We may actually have presentations of some of the papers that were reviewed. So I'm hoping you will come prepared for the discussions. Read and review the assigned research papers and readings. This is very important because we would like you to discuss and critique them online with peers and us. And this is an important way of actually learning the material and getting to do cutting edge research. And we'd like you to write your critique and review online, and we'll talk about that in a separate video as to what is expected and what are some of the suggestions that we have as to how you would review the paper. This is important. Start the research project early and focus on it. The research project will be on the order of 2 to 3 months, and 3 months is probably on the higher end, so optimistically it's 3 months. So you won't have a lot of time, but we will expect a lot from you on this research project, and you will prepare a proposal, which means that you should start the research project right after watching this video. Go and look at potential topics, which we will post online, and try to find projects that you're excited about and that you're interested in and that you have the background for. So it's important that you find such a project and write the proposal, but start it early and focus on it. Don't leave it until the last minute. Don't leave it until the last 2 weeks. Don't leave it until the last month, because last 2 weeks will not be enough for a good project. And the expectations of a good project are high based on the previous project that were done in this course. So you can blame actually the previous students who have taken this course if you would like to, if you're upset about the expectations on the project. Okay, that's a joke. If you want feedback, come to office hours or email us. Obviously, if you're remote, you'll have to email us and we'll have to set up time and you can attend the online office hours. Yes, this may sound like a lot of expectations, but this is how you would get the best out of this course. Okay, I think the last thing I would like to cover in this video is some recommended background videos and lectures. And if you would like to brush up on your computer architecture knowledge, all of the lecture videos from my undergraduate computer architecture course 447 are actually posted on YouTube, and I'll show you the YouTube page right after this. And all of the lecture slides are also posted, and actually exams are posted. Everything related to 447 undergraduate computer architecture course is posted. And I would strongly encourage you to watch as many of these lecture videos as possible and brush up on the background material. And this course will be a lot easier if you actually have that background. Although it's not required that you have that background, having these videos enables you to brush up on this and get a jump start. I would especially encourage everyone to watch, and I will make this a required video, which is the first lecture of my 447 class, which is the basics of computer architecture, because that gives you a broad overview of some of the issues in computer architecture today and why it's important, and also some of the basics of computer architecture. And you can see the link over there, and I will show you the video very soon. There are several other background videos and lectures that I would strongly recommend. Lectures 2 and 3, again from my 447 course, Fundamental Concepts in ISA Trade-offs. So you remember the ISA, Instruction Set Architecture. These are important to brush up on. Pipelining is a concept that I will assume you know mostly. Lecture 8 covers pipelining. Data dependence handling, basically when you have two instructions and when one instruction is dependent on the other one, how do you handle that data dependence to maximize performance is another lecture to watch. It's actually fun to learn about some of these techniques and fun to employ some of these techniques. Control flow handling, control dependence handling, when you get a control flow instruction in the pipeline, what instruction you fetch next, this is the branch problem, is another important topic. And if you would like to brush up on this, I'd encourage you to watch that lecture. How do you handle control flow instructions in different ways? And branch prediction is one method of handling it. That is covered in lecture 11, but lecture 10, whose link is not there actually, talks about other ways of handling control flow instructions.
And you can actually find other lectures that talk about predication, for example, predicated execution. Basically, you convert a control flow dependence, a branch, into a data flow dependence, and potentially have parts of code predicated on the outcome of the branch. Basically, now you have a predicate value, which is a data value that's produced by the compare instruction, which the branch is turned to. And if that predicate is false, the instruction is executed. If the predicate is true, if the instruction is executed. Otherwise, it's not executed. This way, you can eliminate the branch, and that's another way of handling the control flow problem. We will probably get to talk about this, but I'd encourage you to brush up your knowledge by watching these background videos. I'd also encourage you to brush up your knowledge on virtual memory. This is an important topic. Virtual memory today provides the illusion to the programmer that memory is infinite. Basically, that's the illusion. Memory management is not done by the programmer anymore. At least the physical memory management is not done by the programmer anymore. And how to do that, how it's done, is important to look. Okay, and the last 3 lectures that I would recommend are on memory hierarchy, caches, and multiprocessors. Lecture 22 provides an introduction to the memory hierarchy. Lecture 23 and 24 talk about caches. Caches exploit locality in today's systems, and they're very important in computer architecture as well as software systems. So hopefully these lectures will brush up your knowledge on caches. And lecture 30B is on multiprocessors, and I would encourage you to watch the lecture on multiprocessors because some of what we will cover will be on multi-core systems and multiprocessors. Okay, that's the end. I will briefly show you the required, recommended website and lectures. This is actually the website from 18447 from Introduction to Computer Architecture, the undergraduate level course. Some of you have taken that with me in spring 2013. And if you actually go to lectures and schedule, if this internet connection actually works, I think the ECU website is relatively slow, but you will be able to see the lecture. In the meantime, we can go to this YouTube link that I provided earlier, which shows all the lectures from that course. Basically, this will be one of your assignments. You will watch lecture 1, Introduction and Basics, that talk about the beginning, basics of computer architecture. Well, looks like this website is not starting, but you know the website now. You can start doing some background reading if you would like to, and I will see you in the next video.